Last time we talked about the general rules for probability distributions, but this entire section of the class is about nothing but a probability distribution, namely the Boltzmann distribution. So let's apply everything we learned last time to the Boltzmann distribution and see what we can learn. We're going to be able to learn a lot of things, and including some of those things are going to be connections between this rather abstract probabilistic view of things and thermodynamics, something that we know is important and have already spent a lot of time studying. So first of all, we saw from the Boltzmann distribution that all the probabilities are proportional to these exponential Boltzmann factors, and we can normalize it. In fact, we did that up above. And if we do, we see that the normalization factor is nothing but our good old quantity Q, the sum over all the microstates of the system of these Boltzmann factors, exponential factors, e to the minus beta e sub I. This quantity Q, in fact, has a name. It's called the canonical partition function. And we'll see that though here it just appears as a constant, normalization constant. In fact, it plays a very important physical role. It's basically the analog for an open system of W for a closed system. All right, and that gives us then, if we use that, a proper probability distribution, a discrete probability distribution if the energies are discrete, e to the minus beta e sub I over q. We have seen that the probabilities all have to be between 0 and 1, and in fact, the Boltzmann distribution has to obey that too. And if the probabilities are a continuum, then there's a probability density, rho of x. So supposing that the variable, the continuous variable is x here. And that means that the probability density, this much of it, is just e to the minus beta e of x divided by q. But now q, instead of being a discrete sum, is a continuous integral. But otherwise, everything is the same. And in fact, replacing integrals with sums and sums with integrals is a standard thing to do when you're switching between discrete and continuous cases. All right, that's the basics of probability, but we also saw that there are these expectation values associated with probability distributions. That's something we haven't looked at before. Let's see what we can do with that. The most important expectation values for the Boltzmann distribution are those that have something to do with energy. And that's not surprising, right? Because all physical systems have energy as a very important variable to begin with. So taking expectation values for energy ought to be important, and in fact it is. Here's the formula we saw above. The average or mean energy is just the energy of each microstate, I, multiplied by the probability for each microstate, p sub I, and then summed over all the possible microstates in the system. And that formula is correct, and it works, but there's two things. First of all, we'd like to know something more about what the significance is of this average energy. So what? We have an average energy. What good is it? And the second thing is that actually carrying out this sum over microstates is easy if you've only got a few microstates, like most of the examples we've done so far. But we're soon going to encounter cases where there's an infinite number of microstates, and in fact a large order of infinity of microstates. And in that case, this sum, carrying out this sum, becomes absolutely impractical. So we're also going to be looking for a better, more efficient way of actually calculating this average energy. All right, to take up this physical significance first, let's consider a system like we've been considering all along. Remember, all of this stuff for the Boltzmann distribution is for systems with a fixed volume and fixed number of molecules or mole numbers in the presence of a temperature bath. So that's the kind of system we're going to consider. the fact that the volume is fixed and the mole numbers are fixed still allows the energy to fluctuate, right? So there's going to be heat exchanging, and that's going to happen in a random way, so the system's going to sometimes have greater energy, sometimes less energy, depending on how much energy has moved in or out at the moment, in or out of the system. And that means that if we were to take a bunch of measurements, physical, actual measurements on the system, so we're measuring the energy, we take one measurement, we take another one, we take another one, if we do that, we're actually collecting then energies as a function of time. And if we wanted to know the average energy, we would do a time average, right? We'd measure all these energies, E at each time. We'd add them all up, and we'd divide by the however many measurements we made, and that would be our average energy that we actually calculated. Measured, really. But we saw from the ergodic hypothesis before, one part of the ergodic hypothesis is that the time average on measurements made on a system is the same thing as an average over all the system microstates. And if that's true, then this time average we took up here should be the same thing as a probability or an expectation value calculated using all the system microstates. So here we're summing over all the energies of the system, multiplying by however many energies there are at each energy, dividing by Q, multiplying by this weighting factor, e to the minus beta E, and also multiplying by E, right? This is just P of E here. Or equivalently, and in the same way, use our somewhat simpler formula, multiply each energy by the Boltzmann factor, and then sum over all the microstates. So before we were summing over times, now we're summing over microstates, but if we sum over enough times up here, the ergodic hypothesis says we should get the same answer. And so over here I have the time average, the little bar means time average. Over here I have the statistical, what's called an ensemble average, the average over microstates. That means that the actual average energy that we measure experimentally should be the thermodynamic energy, right? And now it should be the same thing as this average energy we computed up above. So this thing up here, it isn't just some random thing we decided to calculate for no reason. It's actually equal to the thermodynamic energy. And this set of relationships that we've just been talking about connects the statistics, is one connection at least between the statistics and the thermodynamic values that we've been talking about for so long already. So this average energy is the same thing as the thermodynamic free energy, and we've got one pretty strong, in fact, connection to thermodynamics. All right, before we go on to talk a little bit more about this, because this is important, energy, you can get anything, you can get other things from energy. So we're going to have to explore that for a little bit. But before we do that, let me point out that if you were to actually make a whole bunch of measurements on our system over time, you can average, that's one thing you can do, but you could also create a histogram of all those energies. And if you did that, you'd be calculating a probability distribution for the energies of the system. In other words, the energy that you actually measure is a statistical quantity, and there's a statistical distribution for it. And the average energy is just one measure or quantity and has much less information about it than the whole distribution does. So the energy is a fluctuating quantity, and the thermodynamic mean energy, the thermodynamic energy, is just a single fixed value. And it's good to remember you can't really see these fluctuations. They're so small on the macroscopic scale that you can't see them. Though if you're doing single molecule experiments, as are commonly done these days, you can actually see them. But in general, if you're not doing a really ultra-sensitive experiment, you can't see the fluctuations, but they're there. And we can even calculate how big they are to some extent. Another thing to say is that when I calculate this average energy using the statistical mechanics that we've been developing so far, then you don't just get one number, you get the average energy as a function of the temperature, the volume of the system, and the mole numbers. In other words, we calculated this average for a system with a specific volume and a specific number of molecules or moles. And you can see right away from beta here that this average that we're computing also has to depend on temperature. And since this average energy is the same thing as the thermodynamic energy, what we've calculated, in fact, is the energy as a function of these three variables, temperature, volume, and mole numbers, and that's a type of equation of state. So not only have we calculated a thermodynamic quantity, we've calculated an entire equation of state. And from that equation of state, we can calculate all kinds of other thermodynamic properties. So we've gone a long ways already towards predicting and calculating all the thermodynamic properties of our system just in this very first go around that we've just done. All right. Now, I said up above that actually calculating the average energy by carrying out this sum over microstates is oftentimes an impractical thing to do. There's an infinite number of terms in that sum, and you can't just do them one by one. Is there an easier formula that we can generate or derive that allows us to do the calculation a little easier? And it turns out that there is. So first of all, notice that this normalization factor Q doesn't depend on the index that we're summing over here, so we can factor it out. And that's what I've done here. And that leaves us with this much. But notice also that this term in the sum is the same thing as minus d beta of e to the minus beta e sub I. In other words, if I took this derivative on that exponential, I would get this, right? Taking d beta would bring down an e sub I in front of the exponential. And since this d beta doesn't depend on the index that we're summing over, I can factor that also outside the sum. And now I'm taking the derivative of all this stuff in the sum, but that's just q. And so I'm really just taking the derivative with respect to beta of q itself. And what's more, if I'm taking the derivative of q and dividing by q at the same time out here, then that's the same thing as the negative of the derivative of the logarithm of q with respect to beta. And that's our compact, more efficient way of calculating the average energy. If you can find, you don't need the whole distribution of probabilities. You don't need all those probabilities. If you can just find the normalization constant, q, then take its log, and then take one derivative with respect to beta, then you get the average energy, which is the same thing as the thermodynamic energy. Notice that q depends on T and V and N, and therefore average energy and also U will depend on T and V and N. So by taking this derivative of this funny thing, the Q quantity, the canonical partition function, we've actually generated a full equation of state for whatever our system happens to be. And there's a point. This is not an accident. The fact that this happened, that we took this derivative and got an equation of state, a very valuable thing, is one example of many other things. It turns out that Q itself is very closely related to the thermodynamics. In fact, Q is the analog for an open system of W for an isolated system. Remember that for an isolated system, W gives you all the thermodynamics. It will turn out, this doesn't quite show that yet, but it will turn out that Q also gives us all the thermodynamic properties for the system. So Q is really important, really central. It's the primary goal. Calculating Q or getting Q somehow is the primary goal of a whole lot of thermodynamic calculations, of statistical mechanical calculations. All right, We've been able to get thermodynamic energy by taking a time derivative. We can therefore get a heat capacity. And since we're doing this for a system with fixed volume, the heat capacity we're getting is a CV, not a CP. So we take the temperature derivative of our thermodynamic energy, holding V constant. That's the same thing as taking the temperature derivative of our average energy, or our mean energy, holding V constant. That's the same thing. I'm just doing a little calculus trick here. It would be more convenient to take the derivative with respect to beta, and I can do it using the chain rule of calculus here, right? I take the derivative of beta with respect to t, and then take the derivative of E with respect to beta, and that's the same thing as taking the derivative with respect to t. But then the derivative of beta with respect to t is just minus 1 over kt squared. So doing the algebra, we get that the heat capacity is equal to 1 over kt squared times the second derivative of the log of the partition function q with respect to beta. So once again, we found that an important thermodynamic quantity is related to this quantity log of q, in this case by two derivatives with respect to beta. That's great, and that's a useful formula, very useful formula. We can use it to calculate another thermodynamic property, the heat capacity at constant volume. But it turns out there's something even better buried in here that isn't obvious at first. To see what that is, let's consider another one of our expectation values. Before we took the mean of E, now let's take the variance of the distributions for E. That means to take a variance, we take the actual energy E, and we subtract the mean value for E. Remember, that's the difference, that's delta E. Then we square it, and then we take a mean or a statistical average after that. Well, if we square this stuff that's inside, we get E squared minus 2E times the average value or expectation value or mean value of E time plus, that's wrong actually there, hold on. Plus the mean value of E quantity squared. And now if I take these expectation values on the outside and do a little bit of algebra, you can see, you'll have to do it for yourself, that reduces to the mean value of the energy squared. So we're squaring the energies and then taking a mean, minus the mean value as a whole quantity squared. So in words, and this is a general rule, it applies for any quantity. We derived it here for energy, but if you've got any other quantity Z, then it's always true that the variance is equal to the mean value of the square minus the square of the mean value. And so in words, the variance is the difference between the mean of the square, right? So here we're taking the mean of the square and the square of the mean. So here we're taking the square of the mean value. So the variance is the difference between the mean of the square and the square of the mean. Okay, if we use that trick now to calculate the variance, first we have to calculate the mean square energy, and then we have to calculate the square of the mean energy. To calculate the mean of the square energy, we use our variance formula. This is the standard formula. So we put an E squared in. There's the probability. I'm dividing by Q out here already. And then I use the same trick I used before. This energy out in front we can get by taking, in this case, two derivatives with respect to beta. And this stuff inside is just Q again. So the mean of the square is just 1 over Q times the second derivative of Q with respect to beta. And the square of the mean means just take minus, right, this is mean E here, minus d log Q d beta, square it, And after doing a little bit more algebra, that gives you 1 over q squared times the square of the first derivative of q with respect to beta. All right, so that's not very useful so far. We have this formula now that gives us, again, a relationship between now the variance in E and all these derivatives of q. But to make that nicer and more compact, let's just try something. Let's try taking the second derivative of the log of q. Instead of the second derivative of q, the second derivative of the log of q. If I do that, here's all the algebra. I won't go through it. I get that result, and if you compare that result with this result, they're the same thing. And so in the end, the variance in the energy, the width of the distribution in energies, the fluctuating energies for our system is just the second derivative with respect to beta of the logarithm of q. Notice that in all these formulas, it's not really q that shows up. It's usually, in fact, in the end formulas, always the logarithm of q. And we'll see why that logarithm of q is always showing up again and again, and later actually in the next lecture. All right, so combining this result for the variance with the earlier result we got for CV, we get that the heat capacity is just 1 over kT squared, so some stuff out in front here, times the variance. The heat capacity and the variance, or the spread, or the width in the distribution of energies are almost the same thing, and it works vice versa too. The spread in the energies is almost the same thing as the heat capacity itself. That's a really fundamental result. The spread in the distribution or fluctuations of the energies is almost the same thing as the heat capacities. And that means that if I can measure the heat capacity, which I can easily do experimentally, then I'm getting something about how widely distributed the energies are inside my system. I'm getting a microscopic measure. I'm learning something about the distribution of possible energies within my system. That's a powerful thing. But the question then is, okay, why that result, right? We've got this, at first glance, a kind of funny result, right? The heat capacity is related to the spread of energies in the system. Why should that be so? Well, here's why. The heat capacity, remember, is the derivative of the thermodynamic energy with respect to temperature at constant volume. What that means is that you get the heat capacity by starting with your system at one temperature, changing it to a new temperature, and measuring how much energy was absorbed in the course of that change. Well, if you're just changing the temperature, you're not changing any of these energy levels, right? Here's our quantum energy levels. This is E0, this is E5 or something. These are all the E sub i's. We're not changing any of those energies. They're staying the same. All we're doing is shifting the population of those states, right? If I increase the population of these higher energy states, then I'm increasing the overall energy of the system. And when I change temperature, that's all I'm doing. I'm repopulating, I'm shifting population up towards the higher energy states, and therefore the system is absorbing energy as a result. Okay, but what happens then if all my energies are the same? If all the energies are the same, remember, for the Boltzmann distribution, that means all the probabilities have to be the same too. The Boltzmann factor doesn't even come in. Everything's got the same energy, all the same probabilities. Now if I change temperature, there's no place to shift energy, any population to. The populations after I change the T are still the same as they were before. If they were all equal to start with, they're still all equal afterwards. So if there's, in this case, there's no, so this would be a case where delta E squared is equal to 0. There's no spread in the distribution of energies. It's the distribution of energies is all peaked at just one value for energy. And we find out that, indeed, that means there's no heat capacity either. Now let's consider a slightly less extreme case. Here all the energies are closely packed together, but they're not all quite the same. Well, if the energies are all packed together, that means their probabilities are all pretty similar too, right? There's hardly any energy gap between the highest energy and the lowest one. They do have some difference in probability. The higher energy states are somewhat lower in probability than the lowest energy states, but not very much different. Now I raise the temperature. I am shifting a little bit of population up towards the higher states, but there's just not much possibility, right? They were almost equal before. Now they're even closer to equal, but there wasn't much difference between the two, and so I have absorbed a little bit of energy, but not much, and so in this case, the heat capacity is small. And so you can see from these examples why the spread in the energy distribution is related to the heat capacity. A small spread in energies means a small heat capacity, but also vice versa. A small heat capacity means a small spread in energies. Now, that's all great. We've derived a couple of fundamental results, the thermodynamic energy or mean energy, and now the heat capacity and the variance of the energy. Let's do an example. Let's do a two-state model. It's always good to look at the simplest possible examples first. Mostly this example is just algebra. There isn't any real deep behavior here, unfortunately. I wish there was. But it's mostly just an example of how to do these kinds of calculations, so let's go through it. First of all, our two-state system just has two states, and furthermore, we're going to set the energy of the ground state to be 0 for convenience, and that means the energy of the upper state is just the gap energy, delta E. We saw before, when we were working out the Boltzmann distribution for this case, that means that the probability for the ground state is given by this formula. It's 1 over 1 plus e to the minus beta delta E. And the population for the upper state is almost the same thing. It's got the same denominator. In fact, that denominator is just Q. And then it's got this e to the minus beta delta E up on top. One way to calculate the average energy, or the mean energy, is just to use the sum formula, which only has two terms in this case. So we multiply the ground state energy by the ground state population or probability. We multiply the upper state energy by the upper state probability. And since E0, the ground state energy, is 0, this term disappears, and we're left with just the second term, and that just turns out to be this. So if you compare all this to all of this, they're the same. That stuff out in front is just P1, and then there's delta E, the energy of the upper state. So that's using the sum. Let's just verify that we get the same answer if we do it using our slicker formula here with the logarithm of Q, the partition function. In this case, the partition function is 1 plus e to the minus beta delta E. So that's our Q. That's what we have to take a derivative with. Derivative of Q with respect to beta is the derivative, and we want to put a minus sign in there, with respect to beta of 1 plus e to the minus beta delta E. And I won't go through the algebra, but you do indeed get exactly the same answer. So our cute, tricky formula works, and that's good to see. Let's also do the standard thing we do whenever we get a new result, and that's evaluate our formulas. These are all functions of temperature, functions of beta, which is just 1 over kT, so functions of temperature too. Let's evaluate these guys at t equals 0, at t equals infinity, and then at some medium temperature. If we evaluate at t equals 0, if we evaluate this at t equals 0, that means beta is equal to infinity. Putting an infinity in there means this top part is 0, and that means we get an average energy of 0, right? And that makes sense because when we're at t equals 0, we've frozen all the population down into the ground state. So here's our two levels. We're all down in the ground state now. And that means the average energy has to be the energy of the ground state, which is 0. If we go to t equals infinity, what's going to happen to the population in that case? In that case, we're going to get equal populations at both the ground state and the upper state. And that means we ought to get an E value in the middle, and in fact, we get just 1/2 delta E. So it's absolutely the arithmetic mean between the upper and the lower state in that case, as you would expect. If our temperature is somewhere in between, so we take the temperature to be one gap size, we set the temperature equal to the equivalent of one gap between the two, then we plug numbers into our formula up here. Here's our formula up here, and we plug beta, we plug the right numbers in. We get e to the minus 1 on top, e to the minus 1 on the bottom. If you do the arithmetic, that gives you about 0.3, 0.27 times the size of the gap, roughly a third of the size of the gap. And that means that our average energy is now a little bit down lower than where it was at infinite temperature, and that makes sense because the population is now greater in the ground state than it was in the upper state. So you can basically see what the average is doing. It's putting the average value nearer to the places that have the higher population and farther from the places with the smaller population. All right. If we do the same thing now with the variance of the energy distribution, or with the heat capacity, then lots of algebra and not very illuminating. In fact, a little bit of trickery in there. And here's the result you get. We'll look at the limits in a minute and see what values we actually get from that. But we can look at the curves for those cases as a function of temperature. And see the whole behavior all in one go. If we're looking at the mean energy, then we get this flat region right down near temperature equal to 0. That's because it takes a little bit of temperature to excite some population into the upper state, right? When you're near 0 temperature, you have no population in the upper state. You've got this finite gap that you've got to get across. You've got to get your KT value up a little bit before you start getting any appreciable population in the upper state. So there's this flat region in the beginning. Then the average energy starts to rise, and you can see a half here is this limit up here. You can see as you go to higher and higher temperatures, you're going to start approaching that limit, which is what we saw before. If you look at the heat capacity, it has this strange behavior. What's going on with that? Actually, this is a little bit unphysical behavior. And that's because we're dealing with this quite artificial model here. We're just dealing with a two-state model. Nothing in real life is actually two states and only two states. So this is a little bit unphysical, but let's look at it anyway. What's going on? Well, if we're at 0 temperature, then we're frozen in the ground state again. You add a little bit of temperature to that, you're still not getting any population up here, and that means you can't absorb any heat, and therefore the heat capacity is 0 down there. And so again, you get this flat region down here near 0. Then as you start raising temperature, you start spreading the energies out, and you get a peak. You eventually get a much higher value for the heat capacity. But what happens if you go on raising the temperature beyond that? Well, you start equalizing the populations now. And now, once you've reached essentially equal populations, it's as if this gap size were effectively 0, right? You've now got so much thermal energy that it's just not paying any attention to this delta E gap anymore. And the populations get equal. Now you change the temperature a little bit, you're not changing the populations anymore. And so the heat capacity goes back down as you start to equalize the populations between the two levels. Again, that doesn't really happen in real life. You don't see a decline in heat capacity as temperature rises, at least not in any system that I'm aware of right now. All right. So that's our simple case for our two new thermodynamic quantities, the average energy and the heat capacity. The next topic is a really important one. We're now going to stop talking about energy, ordinary energy, and heat capacity. We're going to talk about Helmholtz free energy, and ultimately we'll talk about Gibbs free energy. And we know that free energy is a stand-in or surrogate measure of the actual total entropy for a system like this. So when we're talking about free energy, we're talking about the quantity that controls equilibrium. And so talking about free energy is always really important. And of course, when we're doing that, we're talking about entropy too. So let's take that topic up next time, and we're done.